All right, so moving along down through the drinking water treatment process, we've talked about pre-treatment, we've talked about coagulation and flocculation. The next step is going to be what we call sedimentation. So we've talked about sedimentation very briefly when we talked about pre-sedimentation, and they really have the same principles going on in those types of treatment. So what is it? What is sedimentation? So it's a step that normally follows coagulation, flocculation, and it's going to precede filtration. It's kind of the backbone of how we remove particles in a system. So it's a physical treatment process. There's no chemicals added. It's not biological in nature. And it's going to use principles of gravity, viscosity, and particle density to try and settle particles from a liquid suspension. So you have all these particles floating around in the liquid and they're nice and suspended. We now want to have time for those particles to settle to the bottom of a tank. So the main purpose of sedimentation is to focus specifically on the reduction of suspended solids and turbidity. So normally this comes after coagulation and flocculation has occurred, but it's before a filtration step. So we've created floc and we've created particles in coagulation and flocculation, but we don't want those particles to get stuck in our filters. They're going to clog up our filters. So we need to have them settle out of this system. It can also be used to remove iron and manganese after it's been pre-treated. We talked about how aeration can be used to try and create iron and manganese oxides, and those oxides can be settled in sedimentation. So the main purpose of this type of treatment is specifically removing solids. So to help me take a look at how sedimentation works, we're just going to show this quick video, and I'm going to try and make sure I mute it. It's got some strange music in the background, so let's mute that. Maybe not. So the idea is that we have fluid moving into the basin. As it moves into the basin, those solids are going to settle, and sludge is going to form on the bottom, the clean water leaving at the top. And so as these solids are pumped, they accumulate, they're going to have to be pumped out. So at a certain point, we're going to have a sensor turn on probably in the system, and we're going to have solids being pumped out of the system. So I'll play that again really briefly so you can see. There we go. So water comes in the top, and this basin is shaped with kind of a hopper shape. It's got a bottom, basically that's a cone shape that allows us to pull those solids in. So you can see here we accumulate sludge, and it gets to a certain level, and then a sensor will turn on, or somebody will turn on a pump and they'll pump those sludge out of the system. So that's how sedimentation works. So sedimentation basins can look very different. They can be rectangular in shape, they can be circular, they can be square, they can have that hopper shape, lots of different ways that they look. So in the bottom right corner, you're going to see just kind of a diagram of what settling looks like, right? They come in and there's that parabolic arc of solids starting to settle in the system. Up on top, you'll see kind of a circular design where they have these sludge rakes on the bottom to keep that sludge kind of moving. You'll see that the water actually comes in at the bottom, and so the water comes in up at the top, right? It goes in this pipe at the bottom, comes up at the top, everything settles out, and then our effluent comes out the top as well. And so what you'll see in the bottom left is just a picture of what this looks as an aerial view. So you'll see kind of that like dirty water in the middle, and then it starts to settle out kind of on the exterior of this system. So let's talk about some key concepts. So particles settle at different rates. We have different types of particles, so things are going to happen differently when they settle due to gravity. So we have 4 types of settling, and the ones that we normally care about in drinking water at least are type 1 and type 2. When we get to wastewater treatment, we will care about type 3. We rarely ever see type 4 in drinking water and wastewater. So type 1 is what we call free settling. So we have discrete non-floc particles in dilute suspension. So this is like a very pure groundwater source that has some suspended particles in it. It comes in and everything just kind of settles via gravity. Type 2 settling is when we have those like floc particles, those bigger particles, but still in that dilute suspension. So these are this is kind of like what we think of as classic sedimentation and classic settling. Those particles, exactly like were shown in the video, are going to settle due to gravity. When we get to type 3 and type 4, what starts to happen is the particles are so densely packed within a suspension of liquid that they have particle interactions between themselves now. And so they start to hinder their own settling because they're interacting with each other. And so in those types of settling, sometimes we have to add chemical additions, sometimes we have to change the process up a little bit. But type 1 and type 2 are the ones that we see predominantly in drinking water treatment. And particles are going to be settling differently based on their own properties. So things like size, shape, density, and the viscosity of the overall liquid suspension is going to change how fast these particles settle. So in addition to those different types of settling, we also need to remove sludge from the plant, right? So if sludge accumulates in the bottom of our sedimentation basin, eventually that basin is going to fill up and it's not going to work. So at some point we need to maintain we want to maintain that surface overflow rate coming through the system, so we have to have that sludge being pumped out at a specific rate as well. And so you can either design the basin specifically to remove sludge as we go, or it can be pumped in and out. And so you're going to accomplish kind of, when do we remove sludge? By using mass balances and flow calculations. And then finally, basin size is going to matter. So normally we need to know a depth or calculate a depth based on the geometry of the basin. So we might be able to find the surface area of a rectangle, a square, or a cylinder, and then we need to basically figure out how deep does that have to be in order to properly size our basin. So key parameters that you need to know in order to do some calculations when it comes to sedimentation basins. You're going to need to know drag forces on particles. So hopefully you remember fluid mechanics and how fluids move. Normally these are things that we look up, right? I'm not going to ask you to calculate drag force, but something that we need to be aware of. We also need to know particle characteristics. We need to know their density, their volume, and what type of settling each types of particles are going to undergo. We're going to need to know settling velocity. It's something we can calculate. And then we're going to need to know viscosity as well. So how kind of dense the fluid is, how hard it is to move through the fluid. So if we have those parameters, we can do a couple key calculations. So the key calculations we're going to talk about in this class are the volume of the basin. So we'll talk about how do we actually size these things. Excuse me. And then we're going to use what we call Stokes' law, which is based on type 1 and type 2 settling to figure out how to settle particles. So you'll see Stokes' law here. The settling velocity is related to viscosity, the specific gravity of particles, and the diameter of particles. And so we can look up those parameters and figure out how fast are these particles going to settle. We're also going to need our overflow rates. So we're going to need to be able to calculate those based on volume and flow rate. And then we're going to need to be able to interpret what we call percent removal graphs. So over time, you're going to remove a percent of solids very quickly, and then it's going to take longer for some other solids. So interpreting those graphs is a good thing to know as an engineer. So if we want to add sedimentation as a treatment process in our water treatment plant, there's some advantages and disadvantages to this type of technology. So some advantages is that it's a physical process. There's no to low chemical costs. The principles are well established. This is a type of treatment that's been around for a very long time, so the principles are very well established. We know how to design these really well. The main design parameters are related to size. So if you understand geometry, many times you're going to be able to get off to a good start when you design a sedimentation basin. Sedimentation is going to prepare water for efficient filtration. So it's not going to clog the filters, and you're going to have very efficient removal of particles. And it's what I call largely agnostic to chemical addition. So you can add chemicals to the system, and it's probably not going to really affect the treatment process. It's probably going to actually make it better in many cases. Some disadvantages is that sedimentation normally takes up a large portion of your water treatment plant footprint. So it's normally a big component of the system. It's going to require removal and discharge of sludge, and so that might mean that we have to get a discharge permit. That might mean that we have to dewater sludge, and that's all extra cost to the system. And your maintenance can be time consuming on these things. So these are, again, big basins, and if you have to take it offline, you're going to have to drain the entire basin, scrape out that sludge, and so it might be advisable to have 2 sedimentation basins in parallel so you can take one offline at a time for maintenance. So some things to consider if this is a technology you're looking at for a water treatment plant. Last couple things for completeness. We want to know what water or wastewater parameters matter, right? What things really matter for a sedimentation basin. So surface overflow rate, right? Flow rate per cross-sectional area, that's important. Suspended solids concentrations are going to be important. If we want to know how much we're removing, we need to know how much we're putting in. Turbidity is going to be important, and density of the liquid is also going to be important. And then finally, let's talk about some potential impacts of sedimentation. So sludge has to be collected and removed. So most of the time it has to be dewatered because it's going to be very heavy with water in it, and it's got to be removed from the site. Whether or not you can use that sludge for other purposes really depends on what's in that sludge. It could be discharged to the river or the lake if that's your source water, if the correct permit is acquired. So it really depends on what's in the sludge. So a good example of this would be if you're using aluminum sulfate or alum as your coagulant and you have lots of aluminum in your sludge, you're probably not going to be able to discharge that to a river because that aluminum concentration is going to impact the fish. So you have to be aware of kind of how much is in your sludge and what's in your sludge. Most basins are made of concrete, which has a relatively large environmental impact related to CO2 emissions. So one of the kind of new frontiers in looking at sedimentation is looking at different materials for basins. Longer detention times are going to result in a larger plant footprint. So again, sedimentation basins are generally pretty big, and this may be very difficult if you're in a space-limited geography. So if you are in the mountains in Colorado, it's probably going to be pretty difficult to get a big sedimentation basin. So you're going to have to be careful about where you locate your treatment plant if sedimentation is part of that process. And then finally, sometimes these things are outside, right? They're not inside an enclosed building. And so you're just going to have to be able to deal with animals. Birds like to roost in these things, believe it or not. And potential weather events, right? If you have freezing or storms and these things are located outside, that's something you're going to want to watch out for. So that's going to wrap us up in terms of concepts for sedimentation. In class, we're going to focus on how do we actually calculate some of these parameters and put all these concepts into practice.